Hi everybody, and welcome to Unit 4 Part 2 Notes, where we are going to continue talking about the mole and seeing what the mole can do to help us figure out other information about chemical compounds. So today we're going to be focused on what are known as empirical formulas. So first off, just in general, sometimes you have some very simple formulas, and we've seen that in our naming, okay? Things like sodium chloride, things like ammonia, things like water, all right? They're reasonably small compounds, very straightforward, okay? We also certainly have more complex compounds, and one that you should be very familiar with from biology is glucose, C6H12O6. It's a little bit larger of a molecule. All right. When you say C6H12O6 for glucose, you're actually talking about what is known as the molecular formula. A molecular formula gives you the exact elements and the exact number of those atoms in a compound. So again, what is glucose? Glucose is a molecule that has 6 carbons, 12 hydrogens, and 6 oxygens. That is its molecular formula. Empirical formulas give you information, but not quite as much information as a molecular formula. An empirical formula gives you the lowest whole number ratio of atoms in a compound. So let's look up here at glucose. So we have C6H12O6. That's the actual molecule. Well, the smallest whole number ratio, well, what I'm going to do is say, all right, is there a number? What's the largest number that goes into 6, 12, and 6? Well, that's 6. So I'm going to divide all of these by 6, and that's going to give me CH2O. That is the empirical formula for glucose. All right, it gives you the ratio of the atoms, but not the exact number of atoms. Okay? All right. So let's do another example just really quickly. So if I were to give you C4H10, first off, you know that's a molecular formula, okay, because it's not reduced. So that has to be a molecular formula. The empirical for this, well, I'm going to say what goes into 4 and what goes into 10. It's 2. So this is going to be C2H5 is the empirical formula. Okay. All right, great. In general, the ionic compounds that we deal with, all right, things like sodium chloride, all right, or copper 2 sulfate, in general, they're already written in their most reduced form because we did that when we balanced out those charges. Okay, so let's see what we're going to be doing with these empirical formulas. Okay, so we can actually calculate or determine the empirical formula from lab data. And that is because chemical formulas, you should write this down, are mole ratios. So we're going to be able to use the mole. All right, so let's see how this is going to work. Okay, so our first example. A compound is analyzed and found to be 25.9% nitrogen and 74.1% oxygen. What is the empirical formula? All right. So the first thing you're going to do anytime I give you percentages, all right, so step 1, you're going to assume that you have 100 grams. Just to make the math nice and easy. So what that means is instead of just saying I have 25.9% of nitrogen, it's saying that I have 25.9 grams of nitrogen, okay? So step 2, you are going to change from those grams to moles, just like we did the other day. So let's take a look at what this is going to look like, all right? So I'm going to take that 25.9 grams of nitrogen, and I'm going to change that to moles, okay? In 1 mole of nitrogen, again, I look on my periodic table, the molar mass of nitrogen is 14.0. Okay, great. I'm going to stop there and I'm going to put that into my calculator and I get 1.85. You're just going to leave that for a moment. I'm now going to do the same thing for my oxygen. So 74.1, remember I'm changing that percent to grams because I'm assuming I have 100 grams. Grams of oxygen, 1 mole of oxygen is 16.0 grams. I come to there and I get about 4.63 moles. Okay, step 3, and this is a really important step. Okay, you need to know what the relationship is between the nitrogens and the oxygens. Okay, so what you're going to do is you're going to choose the smaller amount, which in this case, the smaller amount of moles is nitrogen, and you're going to divide each of these by that smaller amount. Okay, so step 3 is to divide all by the smallest number of moles. All right, so here I'm doing that. So 1.85 obviously divided by 1.85 is 1. 4.63 divided by 1.85 is 2.5. So that tells me that for this compound, for every 1 nitrogen, I have 2.5 oxygens. All right, great. Well, I can't say that I have half of an atom. So what I'm going to do to get rid of that 0.5, I'm going to multiply it by 2. But whatever I do to one atom, I must do to the other. All right, so 1 times 2 is 2. 2.5 times 2 is 5. So this is going to give me my empirical formula, N2O5. 2 nitrogens for every 5 oxygens. N2O5 is my empirical formula. All right, let's just add to make these complete the last step that we did. And this is an if necessary step, okay? If in this step you had gotten 2 whole numbers, you don't need to multiply by anything. So we're gonna say if necessary, multiply to get whole numbers. All right, fantastic. Okay, all right, so in your notes, we have 2 practice problems. Okay. If you would like to, for each of these, please do what we just did and come up with the empirical formula. All right, pause the video and then go on ahead and do that. Okay, great. I'm gonna go ahead and do this quickly, all right? So the percent composition of lactic acid is 40% carbon, 6.7% hydrogen, and 53% oxygen. What is the molecular formula of lactic acid if the molar mass is 90? Okay, well, Ms. O'Donoghue, why is this asking me for molecular formula when we were doing empirical formula? Well, step 1 is to do an empirical formula problem. Okay, just like we did before. So let's see what that's going to look like. I have 40.0 grams of carbon. Okay, I have 6.7 grams of hydrogen and 53.3 grams of oxygen. All right, I'm going to change each of these to moles using their own individual molar masses. Okay. All right, I'm going to punch those in our calculator, and this is going to give us 3.33, 6.70, and 3.33. When you're doing the empirical formula problems, you always want to make sure you take them out to at least 100ths, if not a little bit more. So remember, our next step then is to divide by the smallest. Don't forget this step. It's really, really important. Our smallest here is 3.33. That gives me 1. That gives me 2. That gives me 1. All right, so my empirical formula for this compound is CH2O. All right, great. I haven't answered the question yet, though. The question asked for molecular formula. Well, here's our new thing to do. So step 2 is you are going to take the molar mass, which I will give you in the problem. I'm going to give you that molar mass, and you're going to divide it by the empirical mass. All right, so how are we going to find the empirical mass? Well, we know what the empirical formula is. We just calculated that. I'm going to find the mass of that. So that's going to be 12 plus 2 plus 16. All right, so that is a mass of 30. I figured that out. All right, great. So here, 90 was given to you. That's the molecular mass or molar mass. Divided by 30, that's our empirical mass. And this should always give you a whole number. And it did, all right? This should be a whole number. All right, so that whole number, what are you going to do with it? Well, you're going to take it and you're going to multiply it by your empirical mass. So I need 3 carbons because C1, so times 3 is 3. I need 6 hydrogens, okay, and I need 3 oxygens. And that is your molecular formula. All right, now that we've gone over this, go on ahead and try and completely do number 2. Okay, try and completely do that number 2. All right, so for number 2, we're going to follow the same process, 58.8 grams of carbon, 9.8 grams of hydrogen, and 31.4 grams of oxygen. I'm going to change those to moles. Doing this kind of quickly, but again, it's just like the problem above. All right. And that's going to give you about 4.90. This gives you about 9.80. And this gives you 1.96, okay? I'm going to divide by the smallest, 1.96, 1.96, 1.96. That gives you 2.5. This gives you 5. And this gives you, obviously, 1. All right, so I have 0.5 here. So remember, I can't have a fraction, so I'm going to multiply that by 2. And if I multiply the top one by 2, I have to multiply everything by 2. Okay. Gives me 10, and this is going to give me 5. So my empirical formula is C5H10O2. I'm going to find the mass of that. Again, just from the periodic table, I'm going to find the mass, and that's 102. I told you that the molar mass is 408. So I'm going to take 408. I'm going to divide it by 102. This should give me a whole number, and it does. It gives me 4. All right, I'm now going to take this 4, and I am going to multiply it by each of the subscripts in that empirical formula to give me the molecular formula, C20H40O8. All right, and then always a nice thing to check is you can go back and find the mass of this, and it certainly should be 408. All right, so a couple last minute things I just want to talk to you about when it comes to these problems. All right, the only numbers, I'm going to make sure that these numbers work out nicely for you when it comes to this multiplying, okay? But let's just kind of talk about the type of numbers you could get, all right? Because you're going to have some different situations with these when it comes to your practice. Okay, if your number ends in 0.5, and again, we can't have half an atom, we're going to multiply it by 2. If it ends in 0.33, all right, to get that to be a whole number, we're going to multiply that by 3. If it ends in 0.25, we're going to multiply that by 4. These are really going to be the only scenarios given to you at this point because we're going to make sure that these numbers really work out nicely for you. All right. There is one last problem in your notes that talks about our next lab that we're going to be doing on empirical formulas. I'm going to hold off on those, and I'm going to actually do that problem at the beginning of the empirical formula lab. All right. So have a great day and enjoy your practice.